Okay, so where we left off in the last video is we're able to confirm that the output of the microcontroller and codec pair was working fine. And the next stage is to get these two op-amps installed, and it's these two op-amps which produce the 0, 90, 180 and 270 degree audio signals that get ingested into the Tayloe detector, Tayloe encoder rather, as this is a transmitter, which will go right here. So what I'll do is get these installed along with the sort of surrounding resistors, and then we'll be able to test the 0, 90, 180 and 270 degree signals at the output here. So let's go and have a look at the circuit diagram quickly and see where that is, and then we'll get started. Okay, so this is the schematic for the transmit encoder, and the op-amp network appears right here. It consists of a pair of LM4562 op-amps. They're pretty good higher quality audio op-amps, and you can see here they're all set up in a unity gain configuration, a unity gain inverting configuration. So the signal at the input gets phase shifted 180 degrees to the output, and there's so you basically tap off the output of the first op-amp, and then the output of this op-amp gets sent to this, gets a further 180 degrees phase shift. The result of which is you're going to get 0, 180, 90 and 270 degrees phase offset of the audio signal right at the output here. Now, I don't need to install these this resistor and capacitor combination here. That's more for the Tayloe encoder itself. So what I'll do is I'll get these op-amps installed together with the 8 resistors that go with that, and then we should be able to have a look at the output here, here, here and here, have a look at that in the oscilloscope and confirm it's has the correct phase shift. So I'll get on with installing those components, and we'll come right back. Okay, so that's the pair of op-amps, which you can't really see that well there, but oh, there we go. Now you can see. So the LM4562 op-amps. There's the 8 10K resistors, which go into providing those unity gain inverting amplifiers. Here's the input caps, the 0.1 microfarad input caps, and then these two are decoupling caps on the power supply. So I've buzzed all this out, and it all appears to be connected fine. So the 0, 180, 90, and 270 outputs I can tap off right here. So here, 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 and finally here. So what I'll do is I'll get some sort of temporary leads hooked up to there, and then we can hook it up to the oscilloscope. I'll inject 1 kilohertz tone, and we should be able to see that nice quadrature output there. Anyway, so let me get that set up, and I'll come right back. Okay, it's a bit hard to see the attachment points here, so you're going to have to trust me on this one. I've got 4 scope probes, and they're each attached to those 4 points that I mentioned in the previous section. I am injecting a 700 hertz tone into the mixer. It's doing the phase shift as before, but now we should see that the full 4 quadrants of the signal. If you have a look in the oscilloscope there, that's exactly what we're seeing. So you can see that. Just let me pan up a little bit. Keeps falling down there. Forgive me. So you can see I've got the 0, 90, 180 and 270 degree signals all there, and in good order. So if I increase the frequency from my signal generator, you can see that the output is also affected. So that means we're good to go and sort of build up the next section, which is the Tayloe encoder itself, consisting of the resistor capacitor network plus the SDR3253. So what I'll do is I'll get those components put on the board, and then we'll come back and we'll be able to do some testing. Okay, before I move on, I thought I'd do something that I always find kind of fascinating. Setup's kind of the same as before, except in this case I'm just probing the 0 and 90 degree output. But instead of having the signal generator just output a 1 kilohertz tone, as you can see here, what I'm going to do is the signal generator allows you to generate a channel on a different frequency on the two channels and add them together. So you can say I've got a 900 hertz tone and a 1 kilohertz tone. I'll add them together. So that's what I'm going to do. So starting with so let's just add a 900 hertz tone and a 1 kilohertz tone. Let's just pause the output. So there's the output there. And you can see there's an interesting 100 hertz beat frequency between the two. But it's a very complex output, and it's very hard to tell just by looking at that, whether it's in quadrature or not. However, you can still go to XY mode and see the output there. And I find this the patterns that it creates with these different frequencies to be very beautiful. So let me just change the frequency. I'll go back to 1 kilohertz. So there's the circle that we see. And then let me go up. So that's 1 kilohertz added with a 1.1 kilohertz, 1.2 kilohertz. And you can see that these beautiful patterns that are generated. And then every time you get it to a multiple of the frequency, so I'm about to go 1 kilohertz and 2 kilohertz, it'll all simplify down into something that looks very interesting. So anyway, I thought you might find this interesting. These beautiful patterns have always fascinated me, but it's just an alternative way of kind of looking at the signal and confirming that it is indeed in quadrature. Anyway, thought you might find this interesting. Let's move on now to the Tayloe mixer. Okay, so quite a bit's happened since the last segment. I've got the quadrature sampling encoder all installed. So there's the SDR3253 right there. The resistor capacitor detector network is right here. I've got that RF combiner right here, and this consists of, this is an FT5043, and there's 10 turns wound bifiller, and then there's a single 20 turn winding on the output. This is a resistor divider to set the center tap of the combiner to 2.5 volts. And what I've done is I'm just tapping off the output of that, and I've got a BNC connector just to basically send that off so I can have a look at it. Some other changes that I've made are I've included this little switch here, which is just attached to one of the pins, so that I can change between upper and lower sideband, and that's simply done in code. I'll show you the code later, but you just simply swap the coefficients around to change between upper and lower sideband. And then finally, on the other side of the board, I've included this. I had a spot for a little pot here, and this will allow me to digitally change the IQ balance between the left and the right channels. Obviously, in a circuit such as this, you're going to get differences in the output network, differences in values of resistances, and so on and so forth. So this gives you an opportunity. That pot gives you an opportunity to digitally adjust the amplitude of either the I or the Q. It doesn't matter which is which, but they're very small. Very small changes. We're talking hundredths of a percent difference in the amplitude. But anyway, that allows me to change that so that I can maximize the unwanted sideband suppression. So what we'll do is we'll get this hooked up to first the oscilloscope and then the spectrum analyzer, and we'll have a look at some of the output. Okay, so kind of as promised, I'll just quickly walk through the code that swaps between the upper and lower sideband. And basically, I've got two instances of first splitter converter, and as you can see, they're almost identical, but with the coefficients swapped around. So this one has the Hilbert, and then the delay, and the other one has the delay, then the Hilbert. And that little button is this bounce SSB, and all you can see is if the button is depressed, then it checks here if the current FIR is USB, it changes it to LSB and vice versa, and then it simply adds it to the rebuilds multi-converter and then adds the appropriate upper or lower sideband. So that's all there is to it. Anyway, let's get over to the oscilloscope and spectrum analyzer, and we'll check out the results. Okay, so let's just quickly go through the test setup. So this is an audio input. I won't be using the microphone for this set of testing. I'll do that a little bit later, but this is audio input coming from my signal generator. And as before, I've got it so that I'm mixing channels 1 and 2 so that I can inject a two-tone audio signal. However, at the moment, it's just injecting a 1 kilohertz tone in here. Off here, this is going off to the oscilloscope, and there is a 50 ohm terminator on the oscilloscope. Here's the SSB button that you saw before. So let's just pan up to the oscilloscope and check that out. So that is the SSB output signal. It does look a bit rough, but you can see so that frequency there is 10.101 megahertz, and I've got the LO set to 10.1 megahertz. So you can see that is indeed an upper sideband signal. Let me change it to lower sideband, and you can see that goes down to 10.991 megahertz. So let's just I'll change the input frequency to demonstrate that further. Let me just change it on channel. All right, so now you can see, now it's a 3 kilohertz tone on input, and you can see the lower sideband signal is 3 kilohertz less than 10.1 or 10.9097. Let me change that to upper sideband, and then you can see that goes up to 10.103. So basically all is looking good, at least on the oscilloscope, for a single tone. So let's try a multi-tone here. Let me just bear with me for a moment while I get this set up. So this is back to this, that's not right. So that's back to the 1 kilohertz tone on input. Let me change one of the inputs down to 900 hertz, and I'll just freeze that. And you can see there's that expected two-tone signal where you have this sine wave that goes to the upper and lower. So this is the expected result, and the beat frequency between here will be the difference between the two tones. So 900 hertz and 1 kilohertz, so that's a 100 hertz beat frequency there. So let's do the traditional 700 and 1900 hertz two-tone test, and then we'll have to pan out a little bit to see that. So you can see it's a bit of it looks a bit of a mess there, but you can see there's a recognizable two-tone output there. And we'll move over to the spectrum analyzer after this, and we'll see what that actually looks like. So anyway, let's move over to the spectrum analyzer now, and we'll check out those signals. So let's start by looking at the upper sideband signal, and just to explain the peaks here. So this is the upper sideband signal, this is the carrier, and then this is the suppressed lower sideband signal. And then you have a pile of other sort of mixing artifacts here, and you'll see more of those as we go into the two-tone tests. So just comparing kind of relative values there. So that's around about minus 20 dBm. So if I go to the carrier, go to the left peak, so that's minus 65 dBm. So that's a suppression of around about 45 dBs between the upper sideband and the carrier. And then if we go to the lower sideband, you can see there's over 60 dBs of suppression between the upper sideband and the lower sideband. So obviously that's pretty good, but it only gets worse from here. As you add amplification
all those harmonics and all those unwanted signals only increase in value. But this is a really good starting point. Anyway, let's have a look at the lower sideband now. I'll click the little button, and you can see that swapped around. So we've got minus 20 dBm for the lower sideband signal, and as I go to the carrier, minus 65 dBm. So similar level of carrier suppression there. And then finally, if we go to the unwanted upper sideband, you can see we've got around about minus 50 dBs of suppression between the lower sideband and the unwanted, this time, upper sideband. Okay, so now let me demonstrate the effect of adjusting that IQ balance pot. So if you'll recall, so there's the IQ balance pot here. Now this in no way directly adjusts the amplitude of the I or the Q signals. It's basically an analog input into the ESP32, and the amplitude changes is done entirely in the digital signal processing. So let's just get back to the spectrum analyzer. So as I adjust the pot, you'll see the unwanted sideband suppression becomes worse. So you've got to find the sweet spot of where the amplitude, the adjusted amplitude is at its best. So as I adjust that down, you can see it's reducing, and around about minus 70 dBm is kind of the best that I can get for this. Now, interestingly, there is a difference. So fortunately, where the sweet spot is for that is the same on upper and lower sideband. But if you'll look, as I swap between those, the unwanted sideband suppression on for the lower sideband signal is worse than the upper sideband signal. So I'm not quite sure why that is. So if you have a look, I go to that left peak. So we're down at minus 76, 77 dBms on the upper sideband, and on the lower sideband, it's around about minus 70 dBm. So not quite sure why that is, an interesting difference there. So let's quickly now move to the two-tone test. We'll do that on upper sideband. And this time I'll be injecting a 1900 hertz tone on one channel from the signal generator and a 700 hertz tone on the other. And so here's the result. Here's the result here. So here's the two primary tones, and then you can see that these are the unwanted lower sideband mirrors of those two tones. But you can see we're getting some other mixing artifacts, the so-called intermodulation distortion, from that. So basically, as I mentioned before, this is directly from the output of the Tayloe encoder, so it only gets worse from here as you apply amplification. As you amplify that signal, these unwanted signals only get worse and worse. Okay, let's finally look at the out-of-band harmonics that's created as a part of the mixing process. And you can see, so over on the left-hand side here, we've got our primary signal here. But you can see, if I move to the other signals, we've got significant harmonics at even and odd multiples of the fundamental. So we've got one here at 20, the next one's at 30. Let's just go over here. The right peak is at 30. Now, one of the things that is typically put directly after the Tayloe encoder is a bandpass filter. So not a low-pass filter. That will come after the PA, but typically after the Tayloe encoder, you've got a bandpass filter. So what I'm going to do is I'm going to wrap the video here. It's running a little bit long, but when I come back next time, I'm going to sort of demonstrate the effect of putting in that bandpass filter straight after the Tayloe encoder, and then we'll have a look at that signal. and then we'll be able to you know, put in a probably a 5 to 10 watt amplifier after that, and have a look at the output again. So anyway, as I said, I hope you enjoyed this video. I'm going to wrap at this point. We've completed the Tayloe encoder. We're ready to move on to bandpass filter, amplifier, and low pass filter in the next video.